So, what I've got here is the past exam 2022 exam 2. I just got it up from where we left off last time we had a look at this. Have you made much more progress on this particular exam? Because if so, I'm happy to move on to a new one.
Yeah, I completed this one already.
Nice. Okay. Was there anything in there worth clarifying?
Not really.
Easy. Okay, cool. So that's 2022 Tech Active, so let's go with 2021 Tech Free. Cool. First couple of questions are always the same, so we'll just sort of skip over that very briefly. It's just find a diff sub in a point, find a diff, well, I guess this is integral, find an integral sub in a point. These are fairly chill kinds of questions. Probably better off to focus on the ones that are likely to be a bit more variant. Like in this case here, question 3 isn't necessarily guaranteed to be a circular function. So let's suss it out. Range of g, that shouldn't be too complicated. Oh, I should probably chuck in the PDF for this one. The answers for this one are still being refined a little bit. I wrote them a while ago and they're a bit incomplete. So, I'll just chuck a working copy in there. They're not going to be particularly pleasant to look at, but at least you'll have something if you need to compare. Okay, range of g. Range being all the possible y values of the function. In this case, all the possible y values of g of x, circular function. How might we go about that?
Could we draw a rough copy of what it would look like?
Yeah, drawing a rough copy sounds fair enough. No worries at all. The main bits, of course, is going to be to figure out where the peaks and troughs are, or at least the heights of the peaks and the troughs. That way, we're able to look end to end and pretty quickly realize what the range is going to be.
Would it be 2 to negative 2?
Yeah, 2 to negative 2. You got an amplitude of 2 with no vertical translation. That's going to mean plus minus 2 for the peaks and troughs. Nice. Period is also going to be relatively quick. It's only calculated one way.
Pi?
Yeah, 2 pi on n, where n is 2, brings you down to pi. Nicely done. This one's also fairly standard, although it has a slight interesting part of it. You're solving a circular function. Yeah, I won't go any further than that. I'll see if you can spot the slightly off thing. It's a bit different.
Is it because there's 2x, so you would have to times 2 to the values you get?
There's a little bit of that going on. Yeah, that's one of the things. It's not the only thing. that's involved there. I feel like as you start solving it, you'll figure out something along the way, and if not, just let me know. We'll work from it there. I might also be making a bigger deal out of it than is actual, so there's also probably that. But yeah, 2x is definitely a consideration.
I got pi on 6 plus n pi and x equals pi on 3 plus n pi.
That's it. Yeah. The other thing that I was trying to allude to is that we're doing a general solution. It's x for all real as opposed to a specific domain. So I was probably over exaggerating. That was a bit unique. Yeah, cool. Well done. That's good. Next up, completely different. Question 4, sketching a graph. Again, that one's going to be kind of tough to describe, so maybe have a stab at drawing it out yourself, and then we'll compare answers. So I'll take away the phone, I'll draw my own version of it, and we'll see if we get the same thing. These sketching ones will usually take some time. That's why they tend to give you a lot of marks for it. 3 marks with, what's it, 1.5 minutes per mark. They give you quite a bit of time. And so I guess one of the things you can do to leverage that is get really, really quick and good at sketching these graphs, so you can save a lot of the time on these higher mark questions. So it's good for people that need the time to make it better, but it's also really good for people who can blitz it out as fast as you can.
Yeah, I got what do you call them? The hyperboles.
Yep. Okay, let's test. So you should have asymptotes at y equals 1, x equals 2. Then y-intercept of 2, x-intercept of 4. Those all checked out?
Yeah.
Nice. Very good. This will actually be nice and helpful for part B, finding all the x values for which the same hyperbola is greater than or equal to 3. I like referring to the graphs when it comes to inequalities. There's a nice visual element to it, which makes it fairly easy to spot. How's that all going?
I got x is greater than or equal to 1.
X greater than or equal to 1. Okay, I know why you got that. Have a look at the graph for now. X greater than or equal to 1. Does that seem to make sense based on what graph we have? So for hyperbola being greater than or equal to 3, it just means that all the y values for whatever your domain is are above or equal to 3. If we have a look at the graph that we have here, like let's say for instance we just draw the straight horizontal line y equals 3, we want to be entirely above this line for the entire domain that we give. That's what an inequality basically says. The reason why you ended up with just x greater than or equal to 1 is because you solved it with pure algebra on that one. Something weird happens when you try to solve the inequality of the hyperbola purely by just looking at the algebra. you would also be well served by looking at the graph as well. Yes, this is going to be the x equals 1 spot, but you can also see that it's going to cut off at this asymptote as well. Fair enough.
Yeah.
I think part of the reason why is because when you're doing the hyperbola inequality, to get the x on its own, you multiply both sides by x take 2. And I think part of the reason why the algebra doesn't fully show the final proper answer is that x minus 2 has the possibility of being a negative number. Under those circumstances, when it could be a negative number, you have to then flip the inequality. So whenever you multiply both sides of an inequality by a variable, I believe you now create two separate inequalities. One circumstance where the thing you multiply was negative, and the other circumstance where the thing you multiplied is positive. In fact, now I'm curious. Let's see how that pans out. We have 1 minus 2 on x take 2 greater than or equal to 3. We're going to have 2 x take 2 greater than or equal to 2. Multiply both sides by negative 1. 2 on x take 2 less than or equal to. Multiply both sides of the equation by that and pretend that that thing was a negative number. Now divide x take 2 3 greater than or equal to x. I didn't really do it, did it? Yeah, I think it's something to do with that. I haven't really looked into this too much. But yeah, the thing that I've found the most easiest is to just sort of refer to the graph itself and then think, oh wait, definitely not going to be what I was expecting it to be. So cutting it off earlier at the asymptote. I might look into that a bit more detail to see what's up. Anyway, next up. Two quadratics share an axis intercept. Find the other axis or x-axis intercept of G. Strangely worded, but yeah, for what it does, it's a strangely worded question. Correction. It did work. I was just bad at math. When you multiply by a negative, you don't just change the inequality. You also still got to multiply by the negative. Yeah, so it did end up actually working out. Spotting that one spot. Anyway. How's this one going? Finding the other axis intercept.
I go x equals 0.
Yeah, x equals 0. Just keep in mind it's a coordinate, not a x value. So when you give your final answer, you want to give the full coordinate, not just the x. But yeah, I mean, look, if you've got an axis intercept at x equals 0, you already know it's the origin. Next up, some transformation stuff. Dilate factor half. Translate 2 to the right. Key thing to definitely highlight there is that dilation factor of a half, because you need to remember that depending on which axis it's dilating from, you may or may not use exactly that number as written as your multiplier. In one circumstance, the dilation factor appears as a division. In another circumstance, it appears as a multiplication. So just keep that one in mind when you're doing your transformation. How's that all going so far?
I'm kind of lost.
Kinda lost? Okay. How far in? So have you done any parts of it yet?
It's like just the transformations, like I've forgotten how to.
Oh, yep, sure. Okay. So I think, correct me if I'm wrong, the way you prefer to do it is you start with some f of x and then you keep shoving in different like little transformations in there over time until you get the thing that you're looking for, rather than like x dash y dash.
No, I prefer the dash
Oh, you do
method.
the dash. Okay, cool. Let's do the dashes then. So with the dashes, we can ignore what the function even is and just start simply by having a look at what the transformations actually are. So in that case, first things first, we got a dilation of a half from the vertical axis. So we're going to start with some initial xy, and we've got to figure out what's going to be that new point. Right? Dilate factor of a half from the vertical axis. What does that look like?
Would the half go in like the x place?
Yeah, the half's going to go on the x, absolutely. Half x comma y. Nice. Next one up. Translate 2 units right. Yeah, translate 2 units right. So what's that now going to look like?
Half x plus 2.
Yep, half x plus 2 comma y. Nice. This is your thing called x dash. This is your thing called y dash. So we have y dash equals y, x dash equals half x plus 2. Cool. Now that we have x dash y dash, do you remember what we have to do from there?
Do we have to make x and y the subject?
Absolutely. Yeah. Y equals y dash. That's a fun one. X dash minus 2 and then times 2 is going to get you x. Cool. We got our x and y as a subject. What do we now do?
We put them in the coordinate form.
In the coordinate form. How do you mean?
Um, because the x. Oh wait, do we sub it into the function?
Oh wait, did you mean to find the axes, as in shift the earlier axes intercepts for coordinates?
Um, no, I just thought like you put it in coordinates, like you go to x minus 2 and then comma y.
2x minus 2 comma y. Oh yeah, yeah. I mean that's another way of representing x dash y dash. That's basically this, except now you got x dash y dash as their own comma. Yeah. No, I thought you meant more so as in like grabbing the old, because that would work if you grab the old x intercepts and shove them into this x dash y dash equation. You will actually calculate where the new x intercepts are of that function. But yeah, the other thing you suggested after that as well is also good, which is f of x. So subbing these into, it was transformed, yeah, transformed f. So we have some function y equals f of x. We're going to replace every y with y. We're going to replace every x with 2x take 2. So that's going to give us y equals 2x take 2 all squared. 2 bracket x take 2 squared minus 4. Now it does say give the rule of h, so I would want to put a little bit of effort into simplifying this. Wouldn't need to be too hard. Probably just distribute that square through to both terms, and then then you've got completed square form, and that's fairly acceptable to have. And then as for now getting those horizontal axes intercepts, you can obviously then just go and sub in y equals 0 for the rest of it. Or what you can do is you can take the two x-intercepts of f and then shift them in the way that in the way that's described. by the transformation. But that would obviously require you to also then find the at least the other x-intercept of f, which isn't hard, right? It's just going to be -2. And so yeah, you'd apply a dilation factor of a half, so you're halving both of those x values, and then shifting them right by 2, so adding 2 to both of them. That'd be the faster way of going about that. Make enough sense?
Yeah.
Sweet. These tend to be a little bit beefy. Good news is they're giving you a lot of blank space to the right of it. At least if you were doing it in the real thing anyway. Yeah, lots of words to suss out there. Let me know how you go. Any luck so far?
I'm just drawing up a tree diagram right now.
Tree diagram's doable. It's probably a bit hard to do it as a tree diagram, because tree diagrams imply some sort of conditional probability with each of them. Like in the sense, you've got like custard, glazed. If you do like custard, no custard, and then branch off to glazed, no glazed, reminder that branches on a tree diagram imply conditional probability. It's doable with it. It's just a bit more challenging to use. This is the kind of thing you'd probably want not a Venn diagram. I mean, yeah, even a Venn diagram actually, but a probability table, the Carnot map, where you've got, like, let's say, glazed, not glazed, custard and not custard, and you do these as all intersections. That'll probably be a bit more understandable. Yeah, I guess the most succinct way to put it is that tree diagrams work really well for things that are done multi-stage or in sequence, whereas there's not necessarily an implied sequence in this. It just sort of has custard and glazed, or not custard or glazed. Yes, technically speaking, there was a sequence involved when when creating the donut. We don't really have any information regarding that. I've pre-filled my table with the key information we were given.
I got 4 and 10.
4 and 10 is correct, yeah. I will say if you're going to give it as a fraction, probably want to simplify the fraction. Whereas if you do them all in decimals, that way you can just sort of get away with saying 0.4, because that just is the answer. I don't think they care too much about it, but it's sort of like getting on the border of being a little bit suspicious, not fully simplifying the fraction. But yeah, I think it ends up being fine most of the time. This one, however, is a nasty piece of work here. I'll give the hint ahead of time. This is where your tree diagrams are going to be quite helpful. So, 20 donuts in the box are now randomly allocated to 2 new boxes, split 50-50. So they're going to be 10 donuts in one, 10 in the other, randomly split. One is chosen, and then a donut from that box is chosen. You got a sequence, right? Box is chosen, then donut from that box is chosen. Here's the challenging bit. G is going to be the number of glazed in box A. And so we're now finding probability in terms of G for a particular thing. If that wasn't bad enough, they also make it a conditional probability. Box B given glazed. So there's a lot of moving parts going on there. The other thing to consider is that this stuff still hasn't changed. Alright, this is still... You can think of these now as global stats for the entire scenario. Like, yes, it's being split into 2 boxes, and so the 2 boxes aren't going to have these, but as a whole, as a collective, these stats still hold up. Lots to consider there. Do you want to try take it yourself all the way to the end, or do you want to start like working through it together?
Can we start working through it together?
Yeah, I think that's appropriate. one of the first steps I would take would be to try and clarify what I'm even trying to do. There's a lot of information there. Good to at least have a nice clear goal in mind. I'm going to write some final answer in there. What probability am I targeting right now? What am I trying to get to? It's going to be PR something as my final answer. What am I actually aiming at?
Box B given G.
Yeah, box B given glazed. Nice. So we'll say box B given G for glazed. Nice. That's our target. Cool. Now I know what I'm looking for. Next up, I mentioned tree diagrams will be helpful here because we saw that there's a sequence involved here. Choose a box, then choose a donut from that box. Cool. So we're going to have our tree diagram set up. So the first stage is choosing a box, the second stage is choosing a donut. As far as labeling these branches, let's look at this first stage. What would I go about labeling this stage as? As in, like, the individual branches.
A and B.
Yep, A and B sounds fine to me. And then as far as our donut selection, a bit harder to maybe tell. What are the two things we're going to be contrasting? When considering that, you should also consider what probability you're targeting, right? Box B given glazed, we would ideally, well, we need to have both information in this diagram. So think about what's missing or how we can represent it.
Would we say glazed and then glazed dash?
Yeah, absolutely. Glazed or not glazed? Glazed, not glazed. Sounds good to me. We got glazed in there, and we got box A and B in there. Sweet. Okay, next stage of a tree diagram is to label the actual branches with their probabilities. So let's suss that out. Cool. So first thing we've got to do is consider probabilities of box A, box B. Probabilities of box A, box B, based on the information provided. What do you think those are likely to be?
Would it be half? Because half of 20 is 10.
Yeah. Yes, we're splitting them 50-50. There were 20 total, 10 are going into both, and so yeah, it's going to be half. No biases here. 50-50 split on both. Okay. Now, more challenging bit for the donuts themselves. G is the number of glazed donuts in box A. So that's going to be a key little thing to consider. Based on that, how can we start putting some labels on the remaining branches?
For like A to glazed, would we go G over 10?
That's a very good idea. Yeah, G over 10, absolutely. There's 10 donuts in the box, G of them are glazed. Probability of being glazed, given that it came from box A, right, because it's a box A glazed donut, it's going to be G. Yeah, that's good. That naturally leads into another probability that we could label. reminder that these are pairs. If I said that this one was 0.1, what would you say this one is?
0.9.
0.9, yeah, why is that?
Because it equals 1.
Yeah, has to add up to 1, correct. The other thing you might consider doing is just saying, oh yeah, it's just going to be 1 minus whatever it was. So for this one down here, this one's g over 10, this will be 1 minus g over 10. You can put it into the same denominator if you want, but we don't really care too much just yet. We're just trying to get information on the table. Yeah, okay. Only thing left is how we're going to get this stuff in here. So you've got G that are in box A, but we don't really have any box B information. Before we find the whole tree diagram, I think one of the principles here is this was probably stuff that was natural to follow in this order. So it was like, okay, what are we trying to do? What's the overall circumstance we have? A, B into glazed or not glazed. We can calculate A and B stuff pretty quickly. We can calculate G and G dash stuff for A pretty quickly. Getting B stuff a fair bit harder. And so this is where I would start pivoting and being like, okay, what parts of this information do I actually need? Now that takes a bit more effort to find stuff. I don't want to be spending time finding stuff I don't actually need. So for me to calculate this conditional, what do I actually need to know?
The intersection with B and G.
Yeah, correct. Intersection of B and G is going to be part of it, that's for sure. So probability of the intersection B and G. The other part of the conditional is the conditional itself. So divided by the probability of glazed. So we need both of these things. Probability of any donut being glazed and the probability of box B intersected glaze. So basically we need to get this, which means we need this multiplied by this. And then probability of glazed, couple ways you could do that. You could find this, which we do know already, and then just add it up with this thing, because you know, you got glazed here, you got glazed here, you just add them up. But we're actually told, we could have found out how many of them are glazed. That would have come from this. If you fill out this entire table, you'll actually get probability of glazed. So this one we could already find, just using table methods. The only thing that matters now is getting this intersection. Pointing towards this table has a secondary benefit. I mentioned earlier that the stuff in the beginning of question 6 is still important for solving this, and that's because you do kind of need to use the information provided in there. The key for getting some G stuff in here, or at the very least calculating this this branch, is to say, okay, cool. I had these 20 donuts, they split 10 in each box. G glazed end up in box A, but there's still some number of glazed that I had in total, right? So one thing that's worth pointing out is probably just it's a good idea to fill this table out, because then you can actually figure out how many of each were glazed, how many of each had custard. All this sorts of stuff come in mind. So filling out that table, I'll just sort of cheat and use the one I've already got. This was your 4, oops, let's make it red so it's easier. This was 4 out of 10, this would be a half, this would be 3 out of 10, That'd be 2 out of 10. And then, so 3 out of 10. I said I was going to cheat and look at the thing, but then it was actually easy enough to fill them all out anyway. Cool. So, to figure out how many glazed we even had, it was 3 out of 10. So we actually ended up having six glazed donuts. Alright, because we started with 20, and 3/10 of them were glazed. They cancel down, giving you 6 glazed. So if G made it into box A, then 6 minus G must have made it into box B. It's a pretty tough thing to spot in the moment. Has it made enough sense the way I've outlined that?
Yeah.
Okay, cool. Because, with that in mind, now we can just do the exact same thing we did over here, right? 6 minus G of them made it into here, so we have 6 minus G over 10, because there's still 10 donuts in each. We don't need to care about this, although we could find it pretty quickly, just 1 minus. And that's pretty much it. So probability of glazed, we can use that 3 out of 10. So 3 out of 10 from that. And then the intersection, well, we're just going to multiply along the branches, and then, yeah, that's it. So B intersecting G is this one, a half multiplying 6 minus G on 10, well that's just going to be 6 minus G on 5. 6 minus G on 5 divided by 3/10. Whenever you have a fraction stack, it looks a bit like shit, so better to split it off as a division symbol instead, and that makes it a little bit easier to see what you do. I still do this, by the way, just to make it easier. 6 minus G on 5 times 10 on 3, and then from here it becomes not much too bad. You cancel down. 6 minus G 3, and you got the 2 from over here. 5 and the 10 cancel into each other, and then yeah, whatever sort of rearrangement or simplification you want to do from there. So that was a lot. Fair enough that fair enough I guess by now how we've gotten to the answer. I'll recap it all.
Yeah.
Cool. Okay. So to recap, that was a lot. That took pretty much all of that working out. And there was only actually 2 marks for it. So this was a fairly intense question. We had a lot of information. They introduced G. A lot of stuff is going on. First things first, let's just figure out what we're even targeting. Donut comes from box B, given glazed. So that should be the first point of call. Start by saying, hey, this is what I want. So everything I do should be funneling towards that. Next up, let's start trying to describe the scenario. We were told that there were 2 new boxes. One of those is chosen, and then a donut is chosen. So we have our 2 boxes A, B, and then whether they're glazed or not. We decided to put glazed or not as the second thing, because the thing we cared about, or the next piece of information we needed, was information about it being glazed. Then from there, we can start labeling some branches. A and B probabilities were pretty easy. 10 donuts went into each, so it's a 50-50 split. G donuts were glazed in the A box, and there were 10 donuts in total. G over 10 for glaze from A. We did end up needing this, but it was easy enough to calculate, so we just threw it in there. 1 minus to get the complement probability. This was a bit harder. So we thought, okay, let's pause, figure out what key information we do need. Any conditional is the intersection divided by the conditional. We already actually had the conditional information, probability of G, or at least we could have had it if we had fully completed the table from the previous question. The only thing left was the intersection. And, at this stage, it was all fairly straightforward, probably except for this bit here, which is to understand we had 6 donuts in total. Right, you had to use this probability based on your sample size to figure out how many of them were actually glazed. And then 6 in total. G went to box A, therefore 6 minus G would have went to box B. even just explaining that, how many bloody steps there are. This probably should have been a 3 marker. That was a lot. Maybe there was something... Nah, not really. Glaze with custard. Yeah, I don't really know if there was a better way of solving that. The answers in the exam report aren't... No, actually, that's exactly what they did in the exam report. Yeah. So, 11% pass rate, by the way. So if you didn't get it, congratulations, you're alongside the other, what's that, 88%. No, sorry, 9. No, 89. I can count. Anyway, that's about it there. If you have any questions to clarify, please let me know. Otherwise, that'll be about it.
Thank you.
No worries.